Section 5.12.2 Three-rotor machine. Let's look at simulating a more practical kind of rotor machine. This machine has 3 rotors and uses the 8-bit UTF-8 code. 3 rotors need 3 substitution tables, S1, S2 and S3. When the rotors are in positions P1, P2 and P3, the nth letter of the alphabet gets enciphered like this. Each of the 3 substitution tables has its own list of steps. Say S1 has steps brackets A1, A2, A3, AI. S2 has steps brackets B1, B2, B3, BJ. And S3 has steps brackets C1, C2, C3, CK. If the sum of the steps for each rotor is an odd number, and I, J and K are co-prime, then the period of this machine is 256 IJK. For example, if I equals 10, J equals 11, and K equals 13, then IJK is 1430, and the period is 1430 times 256, equals 366,080. The effect is like having a polyalphabetic cipher whose tableau has 366,080 rows, with each row used only once per cycle. Suppose the 3 substitution tables and the sequence of steps are known. For example, suppose they have been standardized over a large network. One might imagine that Emily needs to try only the 256 to the power 3 equals 1.67 times 10 to the power 7 initial rotor settings to crack each message. This might take a few seconds on a current-day personal computer. This is misleading. Consider 2 different states of the machine. Both states have the rotors in the same positions, but they are in different parts of the stepping sequence. Starting to encipher from these 2 states will give different sequences of the cipher alphabets, so the same message will be enciphered differently. Cracking this cipher by an exhaustive search would require trying all possible rotor settings and all possible places in the step sequence for a total of 256 to the power 3 times 1430, or 2.4 times 10 to the 10 cases. This is still feasible using a personal computer, but would take several hours, not a few seconds. With known rotors and known step sequences, this 3-rotor cipher is rated 4. If the rotors and step sequences are secret, then Emily must fall back on the techniques for a general polyalphabetic cipher, namely gathering large numbers of intercepts and matching them up to find sections that are enciphered with the same settings. To separate true matches from accidental matches, the index of coincidence test, section 5.7, needs to be done on long overlaps. I suggest at least 200 characters. Matching should be attempted only for messages longer than 200 characters. For a message of length L characters with L greater than or equal to 200, the number of matchable positions is L minus 199. When the combined total M of matchable positions for all intercepted messages exceeds the square root of 2.4 times 10 to the 10 equals 1.55 times 10 to the 5, matching sections of text could begin to be detected. This does not seem like much, but the work to detect these overlaps is on the order of m squared. Moreover, a single overlap is nowhere near sufficient. You need enough overlaps that you can start to distinguish high-frequency letters and separate vowels from consonants. This will require a mainframe computer and some talented cryptanalysts. The 3-rotor machine with unknown rotors and unknown step sequences is rated 6. Section 5.12.3 8-rotor machine. 3 rotors is a good start. To really ratchet up the strength of the simulated rotor machine, let's increase the number of rotors from 3 to 8. Let the number of steps for the rotors be 11, 13, 17, 19, 23, 25, 27 and 31 in some order, and make the sum of the steps odd for each rotor. The period of this machine is about 5.69 times 10 to the power 12. If this is a hardware device, the internal wiring of the rotors and the sequences of steps might be built in. Even if this is the case, it still would not be feasible to match up messages the way we did with a 3-rotor version. This is because there are now 256 to the power 8 equals 1.84 times 10 to the power 19 possible initial positions for the 8 rotors. Since the period is 5.69 times 10 to the 12, the total number of states for the machine becomes 1.84 times 10 to the power 19 times 5.69 times 10 to the 12 equals 1.05 times 10 to the 32. When the rotors and stepping sequences cannot be changed, this 8-rotor machine is rated 9. Let's take this further. Instead of 8 rotors, suppose we have a supply of 16 possible rotors. For each message, we select 8 out of the 16 rotors in some order. There are 5.19 times 10 to the power 8 such permutations. For each such permutation, there are 1.84 times 10 to the 19 possible initial rotor positions, and 5.69 times 10 to the 12 positions for the step sequences, for a total of 5.43 times 10 to the 40 states. Even if Emily somehow knows the substitution tables and the stepping sequences for all 16 rotors, it is not feasible to crack a message enciphered with this machine, even using the largest and fastest supercomputer in the world. At this writing, the fastest supercomputer in the world is the Summit computer, capable of up to 200 petaflops. This 8-rotor cipher is rated 10. If the contents of the substitution tables and the stepping sequences are kept secret or are changed frequently, this rotor cipher with 8 interchangeable rotors should remain far beyond the reach of the largest supercomputers for 10, 20 or perhaps even 30 years to come. Since this is a software simulation of a rotor machine, the rotors can be changed at will. Instead of a fixed set of 16 rotors, the rotors could be changed for every message by using a key to mix up each of the 8-rotor alphabets. This would greatly increase the security at the cost of requiring a separate setup phase for each message. An intermediate level of security is to use 7 standard rotors from the set of 16 and 1 rotor whose alphabet is generated independently for each message. This reduces the setup time by 87%. Even though this cipher has already earned a rating of 10, you may still wish to strengthen it. You might not trust my rating, or you believe your opponent has stupendous computing power available. One way is to use the output of some of the rotors to modify the operation. I suggest taking the output of the 4th rotor halfway through the encipherment and use that character to advance the 1st rotor. Either use the character directly or perform a simple substitution on the character to get the number of positions to advance the 1st rotor. Except for the 1st character in the message, the 1st rotor is stepped twice, once from its stepping sequence and once using the feedback from the 4th rotor. This double stepping does not affect the encipherment of the current character. It is the next message character that is enciphered using this modified setting. Double stepping might be difficult to accomplish with a hardware rotor machine, but it can be done easily with the simulated machine, since the rotors are simulated one at a time. It might seem like it would be stronger to use the output of the 8th rotor, but this is not true. The output of the 8th rotor is the ciphertext character, which would be known to an eavesdropper. The outputs of the 2 middle rotors, that is the 4th and 5th rotors, are the least accessible to an eavesdropper, and hence the safest. This feedback from the 4th rotor makes the simulated 8-rotor machine aperiodic. No matter how many messages are sent, Emily can never find 2 messages with the same sequence of rotor settings.